Well, hello again, everybody. I'm here to help you out a little bit with some homework. We've been looking at our electric motor. And I just want to draw the block diagram for this electric motor again. So the block diagram for the electric motor, it looks like this. We already know you put you have a black wire and a red wire in the motor, and you put that in. Put in a voltage to the motor. There's a motor torque constant, Km. There's a resistance on the motor, Rm, and there's a gear ratio, R2 over R1. When going through this particular block, torque output, torque. Any external disturbance on the motor is also gets summed at this point. We're going to go in here and look at our motor dynamics that we've developed, J equivalent S plus B equivalent. So this takes us, getting a little bit run off the road here. This takes us to the motor speed omega equals theta dot. And then what I'm going to do, I have to make it skinny here because I started, and that gives me theta. That's the output angle of the motor. So I'm going to integrate that. So I've given you parameters for this system. And if what we could do here, in order to just kind of make this a little bit more compact, I'm going to write down what J equivalent is. J equivalent is equal to J of the motor times R2 over R1 squared plus whatever output inertia there is on the motor. In this case, we're going to say there's none. And then B equivalent is equal to B on the motor times the gear ratio, R2 over R1 squared, plus whatever output inertia there is, whatever output damping there is. And then there's always this back EMF, KE, KF, over RM, R2 over R1 squared. So even if there's not explicit damping, there's magnetic damping that goes on there. Now, one of the things that we've done here, we've talked about our magic control law, and what our magic control law is going to do is that we're going to take the desired, theta desired, we're going to subtract the actual theta, and then we're going to just multiply it by some gain. And I've been calling that gain Kp is the proportional gain. Later we're going to find out better ways of doing it. And then as long as I'm just doing this, I might as well go ahead and connect this way. So now I've got a closed loop system. And so my open loop system, my open loop system is in blue. And what I can do is I can talk about my open loop system. T, open loop of S, is equal to Km over Rm, R2 over R1, 1 over J equivalent S plus B equivalent 1 over S. So one thing I want to just point out here, there's some constants and that sort of thing involved here. What I'm going to point out is that this is a type 1 system. Type 1 system, what it refers to, what we're talking about here is that there's one free integrator. If there were two free integrators, it would be a type 2 system. The last time we talked about the transfer function from the voltage to speed, we saw that it was a type 0 system because there's no free integrators. Now, I can put numbers into this. So there's two things that are going to happen here. One is that we're going to look at the theoretical stuff, and then we're also going to look at numbers. Now, I've given you a list of numbers here. Let's see. Should I write those here now? These are for a motor system that I've used extensively in classes for the Quanzer motor system, Q-U-A-N-S-E, Quanzer motor system. I don't know if their parameters are the same anymore. R2 over R1 is 14:1. That's the gear ratio. The motor torque constant, the motor inertia is 3.9 E minus 7. That's in kilogram meters squared. The resistance on the motor is 2.6 ohms. Km is equal to 0.0767. That's in Newton meters per amp. So also Ke, the back EMF, is also whoops, I left a 0 out of this one, 0.00767. And this one is volt seconds per radian. So I've done that. You can show that these two are the same number somehow, but I've done it once upon a time. It's tedious. All right. So if I plug everything in here, I've got an open loop system. I'm going to look at my open loop system here. I'm just, let's do it this way. So the first thing I'm going to do is just neglect the disturbance. And now I can make my closed loop system just look like this, theta desired plus minus, here's my Kp. I'm just going to put numbers in if that's okay with you. This is 0.04134135. You can put your numbers in if you want. This is a 7.644 E minus 5 S squared plus 0.00446 S. Theta. I'm going to do one more iteration of this because this is so a lot of times this is the kind of thing that happens. You can see there's like some small numbers in here, and maybe that's not the right way. Maybe we would like to get this so that it's in canonical form. And if we put it into canonical form, maybe some of this stuff gets to be a little bit less crazy. This is here's Kp. This is 541 over S squared plus 58S. Okay? Now I'm going to switch over here. I guess I'll try and cut this part out because it's a little bit tedious too. Okay. So let's start over again with our system. We have theta desired, Kp, 541 over S squared plus 58S. This is theta, and here's our closed loop system. Now, we're going to use our loop formula, plus minus, to find out that our transfer function, our closed loop transfer function, is equal to, it's the numerator. So I'm going to show you a little bit of a trick here now. So let's see if we can straighten that up a little bit. So so it's the feed forward over 1 plus the feed forward times the feedback. Now, what is the feed forward? So the feed forward has a numerator of g, and it's got a denominator of g, divided by 1 plus, so the feed forward, there's a numerator polynomial in S and a denominator polynomial in S. And the feedback, likewise, can have a numerator of h over the denominator of h. So we could just put it in more generic forms. And then what we can do is, again, let's clear that fraction. We'll multiply denominator of g, denominator of h, numerator of g, numerator of h. And that's going to give us the numerator of g times the denominator of h, divided by the denominator of g times the denominator of h, plus, you know, a lot of times people, one thing that people sometimes do, and I think it's probably worth doing here, is to put a kp here. Sometimes people break out this kp as separate. I'm going to just do that here because it'll be useful for us later. This is going to be kp times the numerator of g times the numerator of h. Okay, so here's a different formula that you can use for your closed loop to resolve a loop into a overall transfer function. So here's the closed loop transfer function. In terms of S is going to be theta, what comes out, over theta desired. That's what goes in. And it's going to look this way. This is going to be the numerator of G, Kp times 541, divided by the denominator of G. Now, numerator of G times the denominator of H, so that's just 1. Do you want me to put a 1 here so we make sure that we've gotten all the parts? So now I'm going to look at the denominator of G, which is S squared plus 58S, times the denominator of H, 1, plus Kp times the numerator of G, 541, times the numerator of H, which is just 1. So now I can look at this as a little bit different. This is a Kp times 541 over S squared plus 58S plus Kp times 541. So here is my closed loop transfer function. I can always look at omega n squared is equal to Kp times 541. I can look at 2 zeta omega n is equal to 58. Sometimes people resolve this stuff into zeta is equal to 58 over 2, 1 over omega n, which is going to be 58 over 2, 1 over the square root of Kp times 541. So I could do it that way too. So I might ask myself, what does the closed loop response look like? And since I know that the closed loop response is basically governed by the damping ratio and the natural frequency, then I'd like to find out what the damping ratio and natural frequency are. So, So now I have to say, what is S? What is S anyway? So S is a complex number, and some specific values are the roots. Some specific values are the roots of the characteristic equation. Now, let's take a look at what those roots might look like. Let's take a look at it. So if it's right, so what we know is that in this particular case, the characteristic equation is S squared plus 58S plus 541 Kp is equal to 0. That's the roots of the characteristic equation. We know that root 1 and 2 are equal to minus zeta omega n plus or minus this omega n square root of zeta squared minus 1. This is if zeta is greater than 1. Or we can say that R1 and 2 are equal to minus zeta omega n plus or minus I omega n square root of 1 minus zeta squared. This is if zeta is less than 1. So I'm going to put an asterisk by this one because this is the most interesting case. However, there are some cases where we're going to have to find out what the roots of the characteristic equation are. And so one of the things that we can do is, well, first of all, let's just take a look at what happens when the roots, when we look at what the roots are. So let's look at the roots here in the S-plane. That's a joke. Did you hear about that snail that has the really fancy Mustang? Yeah, look at that S car go. Okay, so this is, well, one of the things that we know is that this is the real and this is imaginary. Well, I kind of made this already too big because, well, one of the things that we know is that any roots on this side are bad. So these roots on this side, the response, whether it's a first order response that just blows up, or whether it's a complex response that has an envelope that just blows up, either way, that's bad. So what we're looking at is anything in the complex plane, we want to have them on the left half plane. This is where roots are good. So let's look at a root that is here. And what we say with roots that are here, these, because, you know, we talked about this a little bit when we did our analytic solution. These have a slower response. So when I have a root that's out here, this one's going to have a faster response. So all these things are kind of relative. So typically when you get into the region of the S-plane, you know, these are slower responses. It takes longer for things to happen. So, you know, you might look at a first order response. In this particular case, we might look at the first order response. Let's look at it for a unit step input. It would be really slow. And in this case, we'd look at a fast order response. Right, so it's going to be faster. Now, anytime there happens to be a root in this spot, this is complex plane, so this is the real part of S, which is minus zeta omega n, right? We know what that is. And this one is the imaginary part of S, which is equal to I omega n square root of 1 minus zeta squared. Right? So we know what that is. And what's more, so it turns out that we can just draw a vector from the origin to this point in the S-plane. So that is the vector S equals, so this is the vector, so if this is S minus R1, right? Because S minus R1 equals 0. When S equals R1, it equals minus zeta omega n plus I omega n square root of 1 minus zeta squared. Right? So we might want to ask ourselves, just for the curiosity's sake of this, like, how big is S? How big is S? Well, we can just use Pythagorean theorem, right? If we're going to use this as we can use this as the magnitude of S is equal to the real part of S squared plus the imaginary part of S squared square root, right? So let's just do that. This is going to be, so the magnitude of S is equal to, so let's see, the real part is zeta squared omega n squared. So I get to get rid of that minus sign there. And the imaginary part is going to be minus, so we're not worrying about the I part here because we're just looking at the magnitude. So that's going to be plus omega n squared times 1 minus zeta squared. Right, so I squared the omega n and I squared that part, and now we have to take the square root. And it turns out there's some simplification that happens here, which is kind of nice. Zeta squared omega n squared plus omega n squared minus zeta squared omega n squared equals omega n. The magnitude of S is omega n. So the length of this vector from the origin to pointing at the specific location in the S-plane is omega n. And then we might also ask ourselves, I wonder what this angle is here. What is the angle right there? So let's see. I never could do anything until I learned about Chief Sokotoa, which tells me the cosine of theta is equal to adjacent over hypotenuse. So that means the cosine of theta is equal to the adjacent, which is minus zeta omega n. This doesn't have this is just the magnitude over the hypotenuse, which is omega n. The cosine of theta equals zeta. Zeta is equal to the arc cosine of theta. Right? So one of the things is that we can tell when theta starts getting down here, the arc cosine of theta is equal to 1. And the arc cosine of theta, that means zeta gets to be 1 or bigger. And we also know that when angles get up here, that the arc cosine of theta is, it starts getting to be 0, which tells me that zeta starts getting to be big. So now we're getting big on our zeta, right? And so what this tells us is that we can just now look in the S-plane and kind of figure out some characteristics of, if you tell me where the roots in the S-plane are, I can kind of tell you something about them. Okay, bad. First of all, we know that's bad. These are slow. If they're real, they're overdamped, right? Anything that's way out here, fast. If they're complex, see the envelope here is still fast. And they might oscillate with some damping ratio. We can tell what the damping ratio is. Moreover, if things get way over here, these are way underdamped. So without any more than that, you tell me what the roots of the characteristic equation are, and I can give you some information about what the response of that system is going to look like. And that's important. Okay? Okay, so now we're ready to go back and take a look at our motor system that we've been working on for quite some time now, because it's a pretty good kind of standard system to maybe use. So let's look at the block diagram again. H4. So here is theta desired plus minus. Here is Kp. Here is 541 over s squared plus 58s. And here's theta. We know that the transfer function for this system is equal to Kp times 541 over s squared plus 58s plus Kp times 541. And so what I'm asking you to do now is to just make a little table. Kp equals, oh, here, let me make the table here. Kp, R1, R2. Well, here's an interesting thing. I always like to pick the easy ones first. Let's make Kp equals 0. Guess what the roots are? One of them, like you can see by inspection what that root is. S equals 0 and S equals minus 58. That's easy. You don't even have to do any MATLAB commands to find that one out. So let's look at the S plane. And let's look at the real part and the imaginary part. And let's go through, and one step at a time. Let's go through one step at a time here. And let's find out where the roots of the character, well, we just found these roots. This is S equals 0, and this is S equals minus 58. So we can tell this is a real response. This one's really, really, really slow because it's real close to the origin. In fact, it's a special case, but we'll talk about that a little bit later. And then we can choose some numbers here. So I don't know what number's 0.1. I'm going to put a little question mark. Should I put 1 there? Should I put 2? Put 5? Maybe I put 10. And then what I'm going to do is I'm going to draw the roots of the characteristic equation in the S-plane. And I'm going to see what the response looks like, right? I can tell you, if the response starts getting up into this region here, you know, if this happens to be theta equals 45 degrees, that tells me that zeta is equal to 0.707, just a little bit of overshoot there. And that the magnitude, this is omega n, that's the magnitude of that vector, right? So I know those sorts of things. And what I'm going to see is that because there's a free integrator in here, that means that the steady state error, t, of s equals 0 is equal to 1. Why is that important? It is important because that means that t of s equals 0 is equal to the output over the input. That's what the transfer function is. It happens to be equal to 1. That means the output is equal to 1 times the input. That means when you tell it to do something, it does it. Isn't that nice? Okay. So now let's go one step farther with all of this. And what we'll do is I'd like to go back to the beginning. This is all the way back to the beginning, because now that we know how the system responds, I also would like to see how it responds in the face of a disturbance. So let me just see. I'm not sure I've calculated all of these numbers here, but let's just try it again. Uh-oh. Oh, bang, something that I shouldn't have. Okay, so let's try it this way. So here is theta desired. I'm going to redraw this. You know, block diagrams are fun to draw, so you just can't ever draw enough of them. Here's Kp. So this is what generates the voltage. This is our control law. It tells us how to wiggle the voltage to make the system do what we want it to do. And what we've got here is this is a Km over Rm, R2 over R1. Then we've got our disturbance coming in here, plus disturbance. And then we've got our 1 over J equivalent S plus B equivalent. I'm just going to break this up this way because I like to do it this way. 1 over S. This is omega. This is theta. And then we can close the loop. Now, I'm going to redraw this one more time. And this time, what I want is I want to use D as the input. Right? So I'm going to start here. D plus, so D plus plus, and then I've got 1 over J equivalent S plus B equivalent. Can I just do S squared in S? I guess I can just do this now. And this is theta. But now I have to follow this back. So theta, I'm going to follow it back in a specific way. So this is minus, and this is plus, and here's theta desired. I have to put my Kp in. I have to put my Km over Rm, R2 over R1. And now it's clear that I have my feed forward and my feed back are a little bit different in this case, right? Here is the feed forward, and here is the feedback loop. Right, so feedback. We can still do the overall transfer. I'm going to put this as TD of S. So this is the transfer function that is the disturbance transfer function that tells us how does theta move as the D moves. And I'm going to say this is going to be, I'm going to say it's the numerator of G times the denominator of H. So this may get a little confusing because I have RMs and R1s in the denominator, but I'm just kind of treating this as a constant, so it doesn't have S's in it. So I just treat this whole thing as being in the numerator. So it's the denominator of G, numerator of G times the denominator of H divided by the denominator of G times the denominator of H plus Kp, plus, no, there's no Kp, plus the numerator of G times the numerator of H. All right, so let's just do it this way. So what's the numerator of G? 1. What's the denominator of H? 1. What's the denominator of G? J equivalent S squared plus B equivalent S times the denominator of H, that just happens to be 1, plus the numerator of G, which is Km over Rm, R2 over R1, Kp. Now, I want you to go back and look. I may not have, when I broke this down into its equivalent transfer function, you might have to do this one. You might have to close this loop yourself to get T sub theta equals. I'm going to leave that a question mark for you. But what you're going to see is that this is the same characteristic equation. All right? And so for each one of these, points that we have in our little table, we kind of have to look at two outputs, right? We kind of have to look at T sub theta. What does that look like? What does that response look like? Time, position. And we also have to look at T sub D, where we're also going to look at time and position. Now, For a unit step input of the disturbance, what do we, we already know, we looked at the steady state value, this is 1. So when we look at theta, let's just say it's nominally damped. We get, for a unit step input, we get an output. What do we want the disturbance to look like? Well, we really want it to look like 0. So if you put a disturbance on your system, we really want that to look like 0. So I'm going to let you figure out how that works. Okay? All right, very good.